particular modeling technique. In particular, for looking at part of speech tagging, but it can be used for lots of different things. But because we've been talking about part of speech, that's going to be the one I'm going to concentrate on. Technically, you can replace the things I'm talking about, HMMs, with some form of neural model, but we're going to be a little bit more exact with HMMs. In the neural case, you're probably not going to get actual probabilities, but let's not worry about that in the short term. We've already talked about that if we're trying to model things in the word domain, there's an awful lot of words. Okay? And what we like to be able to do is we like to be able to simplify the sequence so that we can share information, so that we can get better models of prediction. So rather than deal with all of the possible different words, if we could simplify them in some well-defined, structured way, then we'd be able to get better language models, we'd be able to make better predictions, and to have better generalization from the data that we actually have. So, what we hypothesize is a good way of doing this, and from experience it does seem to be that it is if we could replace the words with their part of speech tags, part of speech being things like nouns, verbs, adjectives, determiners, conjunctions, etc. If we could replace those, then we'd get better prediction, we'd get better training, we need less things to train, we'd be able to do other things, we get generalization. Lots of things could be better if we actually do that. Now, the problem is, actually, the reason that it's better is because it removes some ambiguities in words and actually identifies their use a little better, and therefore reduces the complexity. We talked about complexity before, and therefore just makes things easier when we're actually doing them. So we take this constructed sentence, okay, Bill directed plays about English kings, and we try to worry about what the part of speech tags would be. We can look at each individual word there and identify which part of speech that word in isolation could be. So we look at the word bill, okay, the word bill can be used as a proper noun, it's a shortened form of William. It can be used as a verb, bill, okay, and that means I'm going to charge you some money, okay, and bill that to me, okay. And it can also be used as a noun, the piece of paper that's got how much money you own, okay, your electricity bill, okay. And so these are three part of speech tags that the word bill could be, and we don't know which one it is, okay, because we haven't found the context it's actually in, okay. Directed can be an adjective, okay, or a verb, okay. So we could have some thing about, I'm trying to think. Could somebody give me an example of using directed as an adjective? So be followed by a noun. I'm trying to think of one. That's why I'm asking you.
A directed study.
Directed study. Thank you. Excellent. Yes, directed study. A study that is directed. Okay, so it becomes directed study, and that's an adjectival form. Plays can be a verb. Okay, and the child plays in the yard. And plays can also be a plural noun, okay, and that's Shakespeare's plays, okay. About can be a preposition, an adverb, or a partitive. English can be an adjective or a noun, and kings can be a plural noun, or it can be a verb. It can be a verb? Oh yes, it can be a verb. How can it be a verb? So, in chess, you could make something into a king, and you could talk about it being kinged, or kings. It's somewhat obscure, okay? And maybe you could make somebody a king, okay? Kingmaker does that, I'm not sure. Despite being European, oh wait, I'm British, I'm no longer European. If I were European, I would know about kings. Okay, so, now, clearly there are different probabilities for each of these possibilities, okay? The word bill has got a probability of being a proper noun, a probability of being a verb, a probability of being a noun, and they're different. Okay? So maybe we shouldn't just take, whatever one is first, we should take the one that's more probable. Okay? But then how would you ever get the other ones, and what would be the point of them if that wasn't true? So we could look at what the probabilities of each of these actually are. So the probability of the tag, let's just look at this left part over here. The probability of that tag for Bill is for a proper noun in some data set that we got this from. It appeared 41 times as an adjective. Wait, sorry, I'm not reading it right. 41 times as a proper noun, 2 times as a verb, and 303 times as a noun. So it's much more likely to be a noun, okay? It maybe could be a proper noun, and it could be a verb, given the data set that this was actually trained on. I don't know what this was actually trained on, okay? For directed, we have 2 choices, adjective or verb. In the data set that we had no directed studies whatsoever, and so it never appeared as an adjective, and it only ever appeared as a verb, and it appeared as a verb 100%, because that was the only one. So why do we even care about the directed? Because we didn't have any example of that. It probably means it doesn't zero, it just means it's small, and we don't have enough examples. And remember we talked about smoothing, and maybe we should care about that. Okay, while if we look at plays, it appears as a verb much more often than a proper noun, and about it appears much more often as a preposition than an adverb or as a partitive. We don't have the rest. Okay, that's just a repeat on that. So each of those are going to have a probability based on the examples we have in some database. So we go and count the number of times. This, of course, implies that we have a data set where it's been labelled with the part of speech tags. So some human went along and said, yep, that's a proper noun, yep, that's a verb, okay? Which is quite a knowledgeable thing to do, and you've got to understand what the part of speech tags are, and it's pretty boring to do, okay? But it has already been done, so you don't have to do it unless we want to do it in another language.
So are the probabilities come from this specific context of text we're looking at, or just from English dictionary?
So it's from some English corpus that we have, okay? And I'm going to randomly guess it from the Wall Street Journal, because most things in language technologies go back to the Wall Street Journal. Because that's what people hand labelled in the 1990s, and so it's probably that, okay? But it's not this specific example, okay? Okay, so for each word we have a distribution of proper part of speech tags, and we can get probabilities of what the expected part of speech tags are. And so for first approximation, we can just take the most probable, okay? But that's, of course, not always going to be right. And actually, there's some information about choosing between these different probabilities that we're sort of ignoring if we just take the most probable one on that word without looking at the context. So we should look at the context. But that becomes a little hard, because depending on what we choose in the context, we could choose that, well, Bill, what's the likelihood of Bill being a noun when it appears at the beginning of a sentence? That's actually a piece of information. Or when it's followed by a verb, that's also going to make a difference, okay? And we like to include that information when we're actually making that choice. But be aware that we don't know whether directed is an adjective or a verb until we've made the decision whether it's an adjective or a verb. Okay, so we make that decision, we could then talk about Bill being a proper noun within the context of being followed by a verb, but if we don't know, we've got this choice, okay? So what we could do is we could basically list all possible forms, okay? So we could take Bill directed plays about English kings, and we could make it a proper noun, adjective, verb, preposition, adjective, proper noun, plural noun. Or then we could change the first one to make it a verb, then adjective, verb, preposition, adjective, plural noun. So we could list out everything, and we get 3 times 2 times 2 times 3 times 2 times 2, which is Okay, a fairly big number, but not a ridiculously big number. Okay, and that's the number of possible sequences we could actually have, and then we could try to calculate the probabilities. Okay, so what we could do is, like, given that it's a proper noun followed by an adjective, what's the likelihood of that, and find out which one's got the highest likelihood, and we could start caring about context of saying what's the likelihood of having a proper noun followed by an adjective. Okay? And that's what we'd like to do. We'd like to make these choices within the context of the choices that we're making. Okay? And because we're making these decisions based on the choices, it sort of makes it a little hard. We could pick the most probable and use that to predict the next one, but that might not give you the most probable over the whole string. It's going to be greedily selecting something that's probable, and that might not be right, or it might be right. Okay? And so what we're talking about today is there an algorithm that would allow us to give the optimal answer for that and be efficient in doing it? Okay? And the answer is yes, there's an algorithm for doing that. It's called the Viterbi algorithm, developed by a guy called Andrew Viterbi, who was a professor of electrical engineering at universities in Southern California, and he is still active, okay, even though he's in his 90s. Though admittedly, he does have to go and work in the School of Electrical Engineering at the University of Southern California, which is called the Viterbi School. Okay, which must be a little weird to go and work in a building that's named after you. I don't have a good name for that. I think that working in a black building doesn't sound quite, it sounds ominous or something. But anyway, but I didn't come up with this algorithm, Andy Viterbi did. And it's used in lots of forms because this is an incredibly common problem. I have something, but I have a choice of things that have local probabilities, but I want to care about some sequence probabilities, but my sequence probabilities are dependent on the choice I make locally. Okay? So I've got this local thing and I've got this global thing, and I'd like to be able to optimize and put these two things together to be able to get the best result. And Viterbi is the algorithm for doing that. And it doesn't really matter whether we're in an HMM type form, or we're in a neural form, or we're in some other representational form of having some local model and some global model, often is a language model. This is the right algorithm we actually want to care about. Okay? Here's the, I sort of talked about this. So, this specific problem, okay, we can actually model as hidden Markov models in a statistical way. And a hidden Markov model is just like a finite state machine, okay, which I'm assuming you're familiar with. A finite state machine has got states and transitions, but what makes it a little different from a standard finite state machine is we have both weights on the arcs, so we actually have some, it's usually a probability on the arcs that are transitioning between them. We also have a probability of being in a particular state, and what we actually also want to say is we have a probability of being in a particular state. So in a finite state machine, you're in a state, you move to the next state, you move to the next state as you get some input when you're doing transition. In a hidden Markov model, the hidden bit is you don't know what state you're in. You're probabilistically in a state. Okay? It's not quantum computing. We can model this with standard computers, and we do. But it basically means for all the states that you have a probability that you're in each of them, okay, and should sum up to 1, but there's probabilities, okay. So you have some probability of being in a particular state. What Viterbi allows you to do with HMMs is find out what state gives you the maximum example at the end. Remember, we've been talking about the noisy channel. Remember that we've been trying to get you to think about cocktails all the time. Okay, when we're talking about things, so we have the blender there with the idea that things are getting mixed up. And you've got these observations, the things that you actually see, and you want to wonder what the underlying form is in the part of speech tags, things that you see in the words, and you're wondering what part of speech tag sequence could best give a prediction of these particular words. Okay, as we've talked about before, there are always these two components. There's the probability of the sequence and the probability of the individuals, and that's what we're trying to do in the part of speech. So this is anything we use a noisy channel for. Viterbi is your friend. It's the algorithm that actually allows you to be able to do these things. So let's go back to our part of speech tagging. And the point is about the part of speech tagging, as we said for the first case, okay, we have an individual probability for each of the proper noun, verb, noun, depending on the word bill, okay. But we also have this other thing about given the sequence that we're in, the sequence we've already chosen, we're going to naively believe that we're going to go from left to right, but you could go from right to left as well. But to go from both sides is a little hard, so we're not going to do that, okay? There are sometimes computational advantages in doing from both directions, but for the most part, you still get the best result if you go either left to right or right to left. So in other words, if you sequence it, you still get the best result. So we're going to go left to right because we are. So we have that component that we saw before, the probability of a proper noun, probability of our probability of a noun, given the word bill. But what we'd like to be able to do is also care about the sequence that we're in. Now we're at the beginning of the sentence. It's a little weird because, in fact, it's almost easy. But what we can say is, what's the probability of a proper noun, independent of the word bill, given the leftness that we have, and the leftness that we have over here is the beginning of the sentence and the beginning of the sentence. Because what comes before the first word in the sentence, the start symbol, what comes before that, another start symbol. So what's the probability? This really means what's the probability of a proper noun at the beginning of the sentence, what's the probability of a verb at the beginning of the sentence, and what's the probability of a noun at the beginning of the sentence. And again, you have to get this from data. So you have to have some labeled data that has part of speech tags in it that allows you to be able to calculate the probabilities of these are trigram probabilities of what these sequences likely are given the particular data that you have. So somebody's taken this, and we're going to pretend it's the Wall Street Journal because it almost always is, of what the probability of a sentence starting with a proper noun, and it's about 20%. What's the probability beginning with a verb? It's about 2%. What's the probability of beginning with a simple noun? It's about 4%. Okay? And so that's important information to be able to combine when you're looking at which of these things you're going to choose. So given that you have the word bill, given that it could be a proper noun, it could be a verb, it could be a noun, but you're at the start of the sentence, you've got more information about choosing which one it's actually going to be. So let's just do them all and not pick the best one at the moment. But we're going to show you something that's efficient about this later. So we've got, three possibilities. What we could do is we could say, well, if it is a proper noun, we're going to have the 20%. If it is a verb, it's going to be 2. If it is a noun, it's going to be 4. We could choose each of those, and then we decide, given those, what's going to happen to the next one. So let's have a look at directed. Okay, it has two possibilities. It's either an adjective or a verb. Okay, and what we can say is, well, what's the probability of being a proper noun adjective? What's the probability of being, well, start symbol, proper noun verb, or start symbol, proper noun adjective? We can actually calculate it and try and find out what that is. We can also have the probability of, given directed, what it actually is, so we can actually get information about that. So we're now getting information about the local information about, given the word, what its part of speech tags are, but we're also getting the particular sequence. Notice what's happened here is we started with 3 things. We now have 6 possible paths, because we had 3 options at the beginning. We have 2 the next, and it multiplies out to 6.
So are we still looking at like individual words, or are we looking in general at what is the probability of being in a part of speech in a particular time given?
So what we're doing is we're combining the information that's local to, independent of the context that it's in. So in other words, what's the probability of the word directed being an adjective? What's the probability of the word directed being verb? And then what we're doing is we're looking at all possible sequences only in the part of speech domain, not in the word domain, to decide what the best is.
So you're handling each thing separately?
Yes.
Okay.
Yeah. Now, you can theoretically do it together. In fact, not just theoretically, you could do it practically together, but you need an infinite amount of data, okay? If you work for Google, not a problem, okay? Of course, you can get an infinite amount of data, but you need a very large amount of data to be able to do that directly, and sometimes that works, depending on the complexity. But it almost always is better if you treat them as two things. Almost always is better, okay? Although some people argue that they don't want to do it. No, they say it's not worth it. It's because they don't want to do it. Don't do that. So what we're getting is these two sequences. We're getting two choices. We've got the localized choice of giving the word which part of speech it is. We've got the information about that. And the other one is just looking at part of speech sequences and trying to find out what the probabilities of part of speech sequences are. Okay? Now remember, the part of speech sequences are independent of the words, and because if we have part of speech sequences, we're going to be able to make better estimates about trigrams in the part of speech domain, because there's only 40-ish part of speech tags rather than a million different words, so it's much more likely we've seen actual sequences, so we've usually got better estimates of what these part of speech sequences actually are than what the sequences of the actual word sequences are, because you need an awful lot more data to be able to do it. That's the advantage of going into the part of speech sequences. So we multiply things out, so we've had 2, and then we've got 3, and then we've got 6 possibilities, and we can continue that to the next one where there's another 2, so we now have 12 possibilities, where we're actually now looking at the word plays, and we're looking at all possible part of speech sequences that can get to the word plays with the two choices of it being a verb or a plural noun, and we can calculate what the thing is. And the best probability so far is the highlighted one, and the 0.00455, which, see if I can put it as a proper noun, verb, okay? Is currently the best. Is it right? Yes, okay, which I don't think is actually right, okay? That's not right yet, okay? But it's being able to choose a number. So we can keep doing this, we can keep expanding things, and we can work out what things are until we get to the end of the particular sentence, okay? Now, this is getting big. It's not ridiculously big, it's not exponential, but it is polynomially increasing, so you're multiplying by the number of possibilities. I suppose it's never going to be more than, if we've got 40 possible tags, it's never going to be 40 times 40 times 40 to the number of things in the sentence, but that's an awful lot, and many words can't be particular tags. But it's still relatively big, okay? But you could do it in modern computers as long as the sentence isn't too long. So what we'd really like to do is to simplify that. So instead of having to do all of the possibilities, can we make decisions at each point about which ones are most likely to give, remember, the greatest probability at the end? So, notice that some of these things down here are much lower than the point 455. And so can we stop looking at those? Is there a way to stop looking at that continued form? Okay. And look, there's some that are 0, okay? And remember that as you're going along, you're multiplying by these probabilities, okay? And if you get 0, what's 0 multiplied by anything else? 0. So it doesn't matter afterwards if we get a really high probability of something, that path's probably not going to continue, okay? So we can get rid of those, which would save us a bit. But actually you can do more than that. And that's what's interesting about the Viterbi thing. The Viterbi thing algorithm actually points out and proves in a in the original paper, that at the particular point that you are, okay, if you take the maximum probability choice at that particular point, okay, you'll get the best result at the end, okay, and that you don't have to care about the paths that are smaller than that, okay, because they can never be better. Okay? It's quite subtle. Well, it's not actually subtle. It's quite believable that it's mostly true. Okay, you take the best things and keep them going. Okay, but actually, it's provably that it's true. And so you don't have to search everything, and you can prune it at every level, and you can get something that's pretty good. Importantly, there are two components of what we're doing here. We have what we call the language model. We've talked about language models. These are the things that, think about them as n-grams. They don't have to be, but they often are. And for this particular problem, the language model is not the word sequences, but the part of speech sequences. Okay? And so what's the likelihood of a particular part of speech sequence to a particular point? Okay? And we have the observation, and what's the likelihood of the word given the tag. So there's these two components, okay, that we've talked about. So we've got these original ones, okay, where we've got the probability of the tag given the word, okay, and the other one is the probability of the sequences, okay, these probabilities are the sequences. And actually what we like to do is we'd like to find the path that's got the maximum or the combination of that. And this goes back to Bayes' rule that we've talked about before, okay, that we like to find the maximum of the probability of the sequence given the words, which we can work out as being the probability of the sequence itself, independent of the words, and the probability of the words given the sequence, divided by the probability of the words. Because we're trying to find the maximum, okay, so the best sequence, we can ignore the divisor because it's always going to be the same, and we're trying to find the maximum over that, so it doesn't matter what that number is, because the maximum will be the same, completely independent of that number. So we can ignore that part. That makes our life a little bit easier. And so we end up with the probability of the sequence of the tags times the probability of the words given the tag. Okay? If you're still awake and listening, you'll notice I'm saying the probability of the words given the tag, while what we had here was the probability of the tag given the word. They're different. I've got them in a different order. Okay? So what I'd really like, in order to use Bayes' rule to join them together, is not the probability of proper noun given Bill. What I'd really like to know is the probability of Bill given proper noun. Okay? It's a different number. Okay? You don't have to calculate anything more, but you do need to calculate something to be able to do that. Okay? So think about it. The probability of a proper noun given Bill, what you'd have to do is look at all the occurrences of Bill in your data set, find out which tag is already associated with it, and look at the probability distribution for the tags given Bill. So you find all the occurrences of Bill, find all the tags that go with Bill, and you look to see which ones are. And there probably won't be many Bills. In fact, in here it says there's only 41 plus 2 plus, so 350-ish occurrences of Bill, so you can calculate what that actually is. Okay? So that's the probability of the tag given Bill. But we want the other way around. If it's a proper noun, I want to know the probability of Bill, which is different. So what I have to do is I have to go and find all the occurrences of proper nouns in the data set and find out which percentage of those is the word Bill. It's going to be a whole lot of proper nouns of other names, okay? But that's a different way that I actually have to calculate. But if you have some data set, you can calculate. Right, so notice, and again, as I've told you often in the Bayes rule, that when you do the Bayes rule into trying to split these into the two components, one of them turns round the other way. Please remember that. And as I've also warned you, 2 times on my slides I get them wrong. Okay? So just be aware of that. In fact, it's really easy to get them wrong. And I think I've already mentioned that sometimes there are published papers that get that wrong. Okay? And actually it still works, but don't make use of that. It sort of still works if you get it wrong, but don't get it wrong. Okay? So, again, back to the noisy channel, we've got a bunch of words that we can see, we've got a bunch of tags we'd like to discover, we have this noisy channel, we'd like to decompose it into 2 parts, we'd like to be able to care about the probability of the tag sequence, and we'd like to care about the probability of the word given the tag, rather than the tag given the word. Okay? So a part of speech tagging task, if you had to write a program to do it, we are not going to ask you to write a program to do this. You should probably use a toolkit to do this, even though it can be fun to write. You've got a sequence of word tokens, so you've got a sentence. Okay. The output is going to be speech sequence of part of speech tags. Why? There's going to be 1 part of speech tag per word. Okay. And you can use HM solution with Viterbi to find the most likely tag sequence given the word sequence. The most likely tag sequence given the word part of speech tag. Okay? And there's going to be these 2 components that we'll be talking about. There's going to be the component of the probability of the tag given the word. Did I get that the right way? Tag given the word. No, the probability of the word given the tag. See, I told you I'd make an error. And the probability of the tag sequence will be your language model in order to be able to do that. The next 3 slides gives you the Viterbi algorithm in various forms, okay? And depending on what you're most comfortable with, you're going to go, yeah, of course. And the other ones you're going to go, next, okay? When I'm explaining an algorithm, I always find it a little hard. I find the best way to understand an algorithm is to implement it. Okay, that's the only way I understand an algorithm. It's very hard to understand an algorithm without me actually implementing it, getting it wrong, debugging it, finding out when it actually works. Okay, therefore, describing it just as the math, well, of course it's right, but to me that's sort of post hoc as the program, the thing that implements the algorithm. Okay, so although I find this utterly correct, okay, I find that's not helpful to me, okay, and maybe you do find it helpful, and if you do, you should read it, okay. But importantly, the things that we're really talking about, again, think about that Bayes equation, think about these 2 components. There's going to be the language model component, and there's going to be the other component, which often has really good names depending on the particular problem you're doing. In speech recognition, it's often called the acoustic model. In translation, it's often called the translation model. In part of speech labeling, it doesn't have a name, which makes it a little hard to talk about, but it's called that model that's caring about the probability of the word getting a tag rather than the probability of the tag sequence. Okay. You can extend the language model longer and longer and longer. Okay, but of course you would need more data to be able to train that. And that might make it better, and depending on the problem and the complexity of the things you're dealing with, that's a good thing to do, or it's not worth it. Okay? For part of speech tagging, trigrams are almost all enough, even for all languages, because the deliberate simplicity of part of speech tags are usually sufficient to be able to just look at a few things round about it, and you don't need the whole sequence. So we can also write it as recursive equations. So basically what we're doing is we're filling in a big matrix, okay, and we're starting in the bottom left-hand corner, and what we're trying to do is we're trying to fill these things as we go along. It's a bit like the the all possible paths that I showed at the very beginning, okay? And what we're going to do is we're utterly dependent on what happened before. So we have to go either left to right or right to left. We normally go left to right. Though that's because English speakers think of language going from left to right. If you're an Urdu speaker or if you're an Arabic speaker, you probably think about it the other way. And that's perfectly okay. If you think about speech, it comes out in one particular order, which is there is an ordering that's natural, that we write left to right or right to left if we're writing an Arabic language. And so we're normally going left to right, but sometimes some things work the other way better, but you can ignore that. And what you're trying to do is you're trying to care about, at this particular point, what's the best possible form that I can actually do it. Okay. So you're going to end up with this big table where you've got all your information of what happened before, and when you're moving to the next form, you're just going to, you just need to record the best at that stage, and you can actually simplify and collapse some of these spanning out, so you can actually reduce things, and that actually makes things much more efficient, and that's what the Viterbi form is. We have a pseudo code for doing it. We can prefer to look at that rather than implement it. There's actually an excellent paper from 1978, which even for me is a long time ago. It's not by Andrew Viterbi. It's by Steve Young, who's a retired professor from Cambridge University in the UK, on the Viterbi algorithm, which was actually the first one I read. I didn't read it in 1978. I'm not that old. I did read it about 5 years later, for the first time I implemented it. For the most part, you're probably not going to have to implement this algorithm. You're probably just going to use somebody else's algorithm. But you should be aware that the Viterbi algorithm is the solution to dealing with these two models of something that depends on a predicted thing that happened in the past, a predicted thing that happened in the past, because you're predicting something and then you're doing some dependent context on that, like in the language model, and the thing that you're predicting, be that translation, acoustic model and speech recognition, or choosing between a bunch of part-of-speech tags. Okay. So remember that for the Viterbi algorithm. Okay. So that's the Viterbi algorithm, and I'm going to move on and talk about some other aspects about part-of-speech tagging, which are actually very practical things that you have to care about. So we're talking about part-of-speech tags, and so one of the things that we actually have to care about is we need the probability of a word given a tag, okay? And we need that to do part-of-speech tagging. What happens if we have to part-of-speech tag something that in a word that we've never seen before? Okay, so we have no data to be able to know what the probability of that word is given a tag. So we suddenly, proper name, suddenly find a new name that we've never seen before. What's the probability of that name given a proper name? Okay, tag, and theoretically the answer is 0. Can't happen. Yeah, but it just happened. Okay, so it really did happen. And so you have to come up with a way of dealing with an out-of-vocabulary word that you've never seen before. There's a number of things that you can do for that. You can sort of say, I just have a small probability for something I've never seen before. Okay? And that can sort of work. Okay? You can also take your data set that you're originally labeling from. You can find really low frequency words and say, this is my unknown word, okay? And I'm going to name it as an OOV, okay? And call it underscore OOV underscore. It's not a word in English, but it's a special tag for words that you've never seen before. And you can talk about its particular distribution, the underscore OOV underscore probabilities. And when you find Nebuchadnezzar, my favorite unknown word, you can actually just say, well, I don't know what that word is, I've never seen it before, I'm going to call it underscore OOV underscore, and then you can call your probabilities and everything works. Rather interestingly, in part of speech tagging, unknown words are much, much, much more likely to be adjectives, verbs, and nouns, and very unlikely to be determiners, prepositions, and conjunctions. Okay? Because determiners, prepositions, conjunctions in English are pretty much closed class. Now what we mean by closed class, as David talked about before, is you can list them. Okay? And so we can list all the pronouns in English, more or less. Okay? I, you, he, she, they, and then there's the case ones of him and her. And we can also have them, and there might be archaic ones like thou and thee, but they're very rare. Okay, and that's probably it. Apart from if you're from Pittsburgh, you've got to have yins as well. Okay, and maybe you have to have y'all. Okay, but you probably do have to have y'all. I think it exists in American English, not just in Texas. I think it's there all over. But there's a relatively small finite set for that. Okay, while if you get an unknown word, it's much more likely to be a noun, verb, or adjective. Okay, it really, really, really is, to the extent that it's probably not one of the other ones. Now, there are some conjunctions which are incredibly rare. Okay, and all these ones that seem almost archaic, like moreover and notwithstanding. Okay, nobody uses those anymore, and if they do, they deserve not to get their part of speech tags out of them. I don't think we should be making judgments like that. Okay? I suppose there could be other. You could also at least potentially think that somebody might use a Latin one sometime because it looks cool or it's appropriate or something, and you've never seen it. So it could happen, but in general, the distribution of unknown words really are adjectives, verbs, and nouns. And so you would take that into account. Now, sometimes you can get more information than that for an unknown word. You, as a human being, rather than a neural network, we're not going to ask the question about whether you are actually a neural network or not, okay? Because that would be an interesting problem. We'd have to take the brain apart and find out, and we're not allowed to do that anymore. But you, when you see an unknown word, okay, one, you take into account what the context are, okay? And if it says Mr. before it, and then you get this name, you think, well, it's probably a person, okay? Because that's what you, although admittedly, you can say things like Mr. President, so it might be a title that you've never heard of before, possible. But it's going to be some sort of name, and you use that information when you're actually doing it. But there's also other things that you do. If it's got a capital letter on it, okay, you think, it probably is proper name. If it's written in all capital letters, you might think, oh, it's some sort of acronym or abbreviation or something, okay? And you're quite good at dealing with abbreviations that you've never seen before and know they're abbreviations, even though you don't know what it's an abbreviation of. Okay? Weirdly. Okay? For example, if you're on campus here and you're told that the class is in something like SHN 203, you immediately know that SHN has to be a building somewhere, okay? And as you all desperately run through all the buildings you know on campus and think, I have no idea which one that is. I made that up, I'm not sure that there is an SHN, okay? But your brain would go, there has to be some building somewhere, okay? Because you know it's a building, and so you know it's an abbreviation, and you're going to try and find it, okay? And that happens in lots of cases, that you're in some circumstance that you're not very familiar with, and you go, that's an abbreviation. So you can do that, okay? Also, if the word ends in ed, or it ends in ing, or it's got an s, well, an s, it might be a verb or a plural noun, but the context, you're going to make guesses about what that word actually is. And we could make the machine do that too, about looking at other information. There are other things about the length of the word, okay? Most of the words you already know are short. In general, the words you don't know will be longer. In general, and therefore you can actually deal with it. And also you can do other things like you all know, you're all at CMU, so you all have a pretty good idea of what the Chinese names are, whether you're a Chinese speaker or not. And therefore you can look at it and go, yeah, it looks like a Chinese name. Or it's this length, and you think, yeah, it's probably a Southern Indian name, because names are this length. Southern Indian. Sorry to all the Tamils, because the way they make their names are different, and they typically take the name and put their father's name on it, and it gets wrong very quickly. So you have these mental models about it, and you can maybe make the machine make these guesses about outer vocabulary. Nowadays, in part of speech tagging, it's mostly solved for English, although people still compete with it. And a standard HMM-based model is probably going to get about 95% correct. The latest fancy neural techniques with extra rules and using multiple models and combining them is probably about 97% correct. The errors that it's making are really in a space where we don't know what the answer is, and almost certainly the original labeling is questionable. Okay, so humans begin to fail. So the examples which are really hard in part of speech tagging are nominal compounds, where you don't know whether it's an adjective or a nominal. So if I say something like a silver spoon, okay, it's not clear whether the word silver, okay, is a noun, the spoon is made of silver, or it's some adjectival form, okay? And you might think, silver spoon, it must be made of silver. No. Imagine you're working in a jeweler's workshop, and they're working with gold, silver, and platinum, and they're forging it in doing things. And when you put the metal into the mold, you have a special spoon to do it, but you don't want to mix the spoons up, because then you'll get gold in the silver and silver in the platinum. So when you're doing silver, you pick up a silver spoon, which is made of iron, okay? And it's the one for silver, okay? And that's perfectly reasonable, okay? You might think, that's not true, but think about this, okay? If a silver spoon is made of silver, what's a fire hose made of? Okay? Or what's it for? Well, you turn it on, it sprays fire into it. Not a good idea. Label fire hose. No. So there's lots of things like that. The other thing that's incredibly hard for part speech tagging and breaks everything is what's called verb particles. We have compound verbs in English. They're somewhat rare, and they often have very special meanings. And they usually have a fairly generic verb, and they have some particle. Okay. So you take the word look. You can take the word look up. Look up is a verb. Okay. So you can look up a dictionary. You can also look a dictionary up. Okay. Which means you put the object inside the verb. Okay. And the up doesn't mean the normal up, as in, you know, up the river or up the ladder. It's a different form. And these are incredibly hard, and almost all part of speech taggers get them wrong. In fact, I'd say all part of speech taggers get them wrong. Next thing is the world is not all English, as you know, okay? And so we need to do part of speech in other languages. And actually, we need the label data. We need to have label data to start off with, okay? It doesn't work otherwise. You need to know truth in order to be able to train things. And you need a lot of data to train, okay? So what do you do for the 7,000 languages that are out there? Okay, we just start working on it, and we pay a couple of $1 million and get people who speak the language, train in linguistics, who make the decisions about whether there's nouns, verbs, adjectives in the language. That's not always easy to distinguish, and decide how to label it. Yeah, we've not done that. We've maybe done it for 10, maybe 20 languages at some level. Google has a limited part of speech tagger that they've done for a large number of languages, and it's pretty good. It's maybe about 20 languages, mostly European, and the big languages in the world, so Chinese and Arabic. Often what people do when they go to a new language is they build a not very good part-of-speech tagger, label the data, and then go and ask linguists to fix the errors. Because it's going to be about 90% correct, okay? And then maybe once they find the errors or the things that could be an error, they try to mine the ones that are an error and go in and fix them afterwards. That sort of works, okay? But you're always subject to the accuracy of the human labelers. And after a while, it's sort of not worth it. You know, you could get the human labelers to fix it, but they maybe don't know, and they might not agree, and there could be different meanings of the same sentence, the silver spoon type thing, that you're not very sure which one it actually is. In languages with morphology, that's almost all the languages on the planet apart from English and Chinese. It's just good that that's not the two biggest languages on the planet. But the morphologically rich languages, in some sense it's easier, and in some sense it might be harder. There are more words in morphologically rich languages because there's variations of the base word. But often these variations are telling you explicit information about whether it's noun, verb, adjective, conjunction, etc. So they've got explicit information that actually makes part of speech tagging easy. Okay. There's usually still confusable cases that you actually have to deal with. But again, remember, we're doing the part of speech tags because there's too many words. We're trying to reduce things to get a better sequence that we can make better recommendations that can generalize over data we've never seen before. Okay? If we had an infinite amount of data for all languages with a good distribution of all the words, we wouldn't need to do part of speech tagging. And if we had free GPUs and really big memory, we wouldn't need to use part of speech tagging, probably. But we don't, so we always want to do part of speech tagging. Okay, so what happens if you want to do this in a language you don't know, and you've been given this problem as a homework and you have to get it in by tomorrow afternoon? What are you going to do? Or you're working in a company and they say, yeah, we're going to do Tagalog, language spoken in the Philippines. We'd like you to do a part speech tag because it's going to allow better models. How can you go about doing it? Well, you can do unsupervised part of speech tagging. It's not ideal, but it still works and could be useful, because remember, the purpose of part of speech tagging is to give you a reduced number of tags where sequences can be more predictable. That's what you're trying to do. Linguistically, okay, it's a good idea to use these linguistic tags that we talked about because they're universal across languages. They have predictive properties that allow us to be able to make better prediction. But yeah, if we could come up with something else that's got some of those properties, especially if it was automatic, that would be okay, especially if your homework's due tomorrow afternoon, or you have to at least get something working. In general, okay, high-frequency words are function words in the language. Okay, so you could look at all the language, you could look at all the words, you could look at word frequency, okay, and the top 20 are function words. Okay, the 20 is not the right number. Okay. But it might be that if you look at that, you could show that to somebody and say, look at these words. Which of these are function words? As long as you explain to them what function words are. But you can usually explain the meaning of function and content words to people in the language, even though they don't know linguistics. They usually get that fairly quickly. But you can actually do a little more than that, and it sort of works. And what you really want to do is find out words that appear in the same context. Okay, so what you'd really like to do is find, on some large corpus, you want a fairly large corpus, it doesn't have to be massive, but at least thousands of sentences or tens of thousands of sentences. What you'd like to know is which words, okay, appear in the same context. So given a word, it's got context before and after. It might be just immediately before and immediately after. It might be the 2 words before and after. Okay, and what you'd like to be able to do is find out, okay, which words appear in the most frequent context. So you look at the words round about them and you try and sort them all out and find out which words appear the most. And what happens is the words that appear in the same context are almost always the same part of speech. So, this seems a little weird. It's not very hard to write, okay, to do this. So you just basically look at every trigram, you take the middle word, you put it out, you take the other ones, you stuff them together and put an underscore between them, okay? And you print them all out for everything, okay? You then do some word count on the things with the underscore in them, okay? And you look to see which words are the most frequent that appear given that context. And then when you do find the top ones that are all together, you say, well, you have to have some thresholds about the number of recurrences. You just say, all of these are the same, I'm going to collapse them. Okay? What we've done for this is I wrote something that's in one of my pattern speech taggers for unknown languages for speech synthesis, so that you can run this and it gives you classes, and it's very easy to do, and you don't need to know anything about the language, and it does it. And what it does is, for one pass, it looks for the most frequent ones and says these are in the same class. Okay? And then you run it again, and if it finds another one that joins that class, it goes in that class. If you do it for English, you get these things joined together. Okay? So you get the word be and you get the word have joined together. They're both auxiliary verbs. You get the word Mr. and Mrs. joining together. They're both titles. They're reasonable to join together. You get the words and, but, at, as together. They're all conjunctions. You get to, for, off, in together. They're all a certain type of preposition. That's okay. You get very, so. They're both intensifiers together. And you get he, she, it, I, you. Okay? And you can see from that the data set that I have was not from Pittsburgh because it doesn't have yins in it. Okay? But we found all the pronouns. Okay? So I've done this for a bunch of different languages. I've done it with the languages I don't know, and it works pretty well. Okay, so if I do it for Chinese and I don't know Chinese, and then go and ask Chinese speakers, are these the same class? And they go, yeah. And so when I do the things I can read in Chinese, gets all the numbers, puts them together, actually gets all the classes of numbers and puts them together.
Wait, well, to clarify, what do you define as context again?
Say the word before and the word after. Okay? You can play with that. You can maybe get rid of morphological variants. You can maybe take 2 words before, 2 words after. It'll depend on the language and the complexity of what you could do for that.
How does the number of unsupervised classes that determines relate to the number of linguists?
That's a good question. So the problem with this unsupervised technique, you don't know when to stop. Okay? You run it, and you run it again, and you run it again. And it continues to put things together. It will always put things together. Okay? And after a while it starts to do stupid things, okay, that you would not do, okay. And I don't know the answer about how to stop. You really probably have to ask a native speaker when it's starting to be stupid, okay. For example, I was doing this on the European Parliament data because we had that for back in the days when English was in the European Union. Actually, it still is, because of the Irish. So we're doing it for lots of languages that are about the same amount. And one of the things it very quickly does is start putting Prime Minister and President into things that it maybe really shouldn't, okay? And thinking that there's a collapse of the word Council and Parliament together, which there is for that data, but not normally. You had a question again?
Yeah. So since this is unsupervised, does that mean that you don't know like which part of speech the stuff you're classifying?
Yes, that's exactly it. They become part of speech 27. Okay, I don't know if they're conjunctions. I don't know if they're pronouns. And in general, this technique does not work for nouns, verbs, and adjectives because these classes are too big. They've got too many different contexts they appear in, and therefore they're never going to bubble up to the top. So almost all the content words end up being in one class. Okay, but I'm going to talk about a solution for that in a minute. Okay. So this gives you lots of things that might be useful and a class of other, and it might, if you're in some language you really don't know and you're trying to make your life easier, unsupervised part speech tagging often gives you something better than no unsupervised, no part of speech tagging, but it's often not as good as actual part of speech tagging, but it's relatively easy to do, and there's lots of toolkits out there that will do something like this. Let's come to the issue of can we actually do more than just the content words? There's a technique called Brown clustering, named after Peter Brown, who was one of the early pioneers of statistical machine translation. He worked at IBM. He has a PhD from CMU, which was not on computation. And what this is completely unsupervised word clustering. Given a big data set, okay, what it does is it does this technique of looking at all the contexts, okay, but it does it exhaustively for the whole data set and tries to work out the distance metric between every word and try and find which word is going to be the closest context for all possible words. The way it does it is it builds it as a tree. So what you actually get is this binary branching tree where the word at the bottom of the tree and the next word up, which will be its sibling, or it might be a cousin or an uncle in the tree, are the closest together. Okay? So what it does is it's trying to measure all possible contexts for each word and then trying to find out how to put them together. The further you go up the tree and all the words underneath are classes, okay? So when you look at the result, what you often find is that one side of the tree is all the function words, and it does the same thing that I talked about earlier of finding the pronouns, finding the conjunctions, etc. But at the other side, it actually puts together all of the content words as well. It can't tell you what the nouns, verbs, adjectives are because it doesn't know where to cut the tree to get that, and it doesn't really get that either. But what it does get is the words that are close to each other in the tree, you think about it as a family tree, closest in that metric, are usually related to each other, such that you'll find some subtree that's got all the colours in it, okay? Or if your data's about bus information, you'll find all of the bus stops will be under one particular form, okay? And that works pretty well. It was originally done for machine translation, for putting things into classes, and so it's pretty cool, okay? And so you have to make some decision about how to splice the tree off into classes, and you could say, I'm going to put groups of 50 words together, and then you could do that automatically. It wouldn't be ideal. You're going to have a fair amount of data before that's going to work. Oh, it's computationally really expensive to run, okay? Just thought I'd tell you that. And it's pretty hard to parallelize as well. So unfortunately, even we've got much faster machines and much more parallel, it's quite hard to do. But there's a number of pretty interesting semi-stochastic techniques that can be used to get pretty good results for Brown clustering out there, and it's often a useful thing to do, okay, depending what you're doing, to give classes to your words. And it does group together things that are sort of semantically similar, okay, sort of semantically similar, okay. The example that gets given for colour, which we'll come back to a number of times, is often the word other is treated as a colour. What? Other? And that's because it's very common to have things that will say something like, it's available in blue, red, or other. Okay? And it also appears in things that says blue, red, or green. And so other often appears in some type thing, okay? And so it sort of looks like a colour. And arguably it is, okay? In some abstract sense, it's an option in the colour field. And so you get funny things like that, okay? You can go to the destination of downtown shopping mall or return. What? Return? Yeah, but you can imagine that that's something like a destination, okay? This is actually called hierarchical agglutinative clustering. It has a name. It is a cute algorithm. It is quite computationally expensive, and we've sometimes been in positions of not running it because it takes too long. But if you have the time, I mean, it might take several days to run. If you're working with artists for a long time, it's a reasonable thing to do. But it is a way to actually reduce things. And you could run it as pre-training and be able to get one and then apply it to something else, but you'd have to care about unknown word. okay? Because if you're applying that, I want to know what the class is for this particular word or its position in the tree, and it might not be in the tree. You'd have to come up with something to do with it. Either you have the unknown word thing where you process your original data, find low frequency words, replace them with out of vocabulary, okay, and then build your brand clustering, and then when you get a word that you've never seen before, it becomes an out of vocabulary, and therefore it gets put in the class of things that appear in contexts which are unknown, which might be, you know, titles, or it might be places, or something like that. But brand clustering is a pretty cool way of at least getting something out of clustering. Okay. Now, these things are quite different from word embedding that we're going to talk about later. Okay. There's maybe some similarity in them, in that you're getting a representation of a word that's not just the word, and you're trying to put things together where there might be a distance metric to tell you how similar they are. But these are a different technique. And in fact, often they're doing a different thing, and so often using both word embedding and some form of part-of-speech tagging, or unsupervised part-of-speech tagging, or brand clustering, or equivalent, is a reasonable thing to do if you want to try to reduce the size of your vocabulary, but still keep something about contexts of things. So what I've talked about today, remember that the whole point about speech tagging is to reduce the number of words to a bunch of linguistic tags, so we get a smaller number of things, so the complexity of our representation goes down, so we might be able to better model it when we don't have an infinite amount of data. Okay? Remember that we've got these two types of part of speech. We've got the closed class ones, which mostly you can name. Okay? And most people can name in the language. Okay? If they know what a determinant is, they can name it. Okay? So determinants, pronouns, conjunctions. And the open class ones, nouns, verbs, adjectives. Adverbs, you can't list them, and that's where the new ones are going to be. Okay? We can do probabilistic labeling. There's good, well-defined probability theory ways of doing it. We can use it with the Bayes equation and noisy channel. We care about the probability of a tag word multiplied with the probability of the sequence of the tag. We can use HMMs, and we can use Viterbi to be able to do this. It's very efficient. It gives you the right result. It gives you the optimal result, I should say. We can discover unsupervised tagging, and one of the things that unsupervised tagging cannot really do is deal with the ambiguity of tags. So if a word has got multiple meanings or multiple uses, most of the unsupervised stuff just doesn't get it. Okay? And at best it gets confused, at worst it utterly ignores it. But remember, at least for English, if you take the most frequent tag and don't do the fancy part of speech tagging, caring about the context, you're going to get about 90-91% correct. And that might be good enough for the task that you're doing. And it might be better than not doing it. Okay? It's not as good as doing real part of speech tagging, but that might not be available in the language that you're actually working. Okay? And one of the things that David and me are trying to get into you, that there's all these tools, there's all these things you can do, but remember, you're building an application. Okay? If your application gets better with this thing, you should use it. If your application doesn't get better with it, you shouldn't use it. Okay? Because you're trying to get your application to be better. Unsupervised tagging clustering exists. It's way better than nothing. It doesn't always do exactly what you want. You do have to care maybe a little bit more about domain. Okay? Brand clustering is great, but only if you have a database of text in the domain that you're ultimately dealing with. Okay? You do brand clustering on Wikipedia and then try to use it to label Twitter data. It's going to be useless. Okay? Even for the words that overlap, it's just not going to give you sensible breakdown. Remember what you is use the best one for your task. So you want to test things to see what actually works for you, not because some bearded professor says to you, "This is really good. You should use it." Okay? You should use it if it gets better. Okay? And of course, if it should get better, and the guy at the front with the beard says it should, and it doesn't, okay, you should either complain, or maybe you've implemented it wrong, or there's probably a reason it doesn't work. Okay, it might be it's not appropriate for the actual domain you're doing, and so think about that. And if you can find a good reason for that, I'm not going to do this. I'm on Twitter. I'm trying to analyse Twitter data. Part of speech tags from Wall Street Journal is not going to work, and that's sort of true. But there's a part of speech tagger for Twitter. Okay, so you should look for that. It's specifically for Twitter, although it's almost certainly out of date because it was done 5-6 years ago. So you know use the one that works. So test things when you have these things available, but be aware that there is these choices to be available. Okay, any questions? Okay, thank you. Okay, class.